Yes. Oh, I mean, I looked into it. My presentation uploaded. Uh, um, just a very small period, it's all right. But after that, I hope the Newton, as I said, part of my results are not the only. I don't have my own, just using it. So, all right. All right. My.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Welcome our audience to lecture and learning session series 45 in the theme Water Resource Management in South Sulawesi. With our speaker, Prof. Hiroki Oe from Ehime University. We know in graduate school, third floor 3, in teleconference room will be live in this room about lecture and learning session series with water resource management in South Sulawesi. Now we have our speaker from Japan, and this event moderator by Ami Sukma Utami, PhD. She is lecturer from the Agribusiness Universitas Andalas. Now we are live to this LLSS 45 with our moderator to Ami Sukma Utami, please.
Okay, thank you Fuad. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone. Distinguished lecturers, students, researchers, and honored guests. My name is Ami Sukma Utami, and it is my pleasure to serve as the moderator for today's section. So for today's learning and lecture and learning session series on water resource management in South Sulawesi. It is a great honor for us to have Professor Hiroki Owe from Ehime University as our speaker today. So Professor Owe has spent many years conducting research in field of water resource management, particularly related to irrigation system for paddy rice agriculture. His expertise mainly focus on hydrometeorology, including water availability, hydrological process, and also environmental monitoring related to agricultural water system. Through his long-term research experience, Professor Owe have been involved in various international and collaborative projects, including several studies in Indonesia, particularly in South Sulawesi and this recent year in West Sumatra. He has also conducted research in Bali also, right, Sensei? And then, so today's topic is highly relevant, especially as many regions are facing increasing challenges related to climate variability, water distribution, and also changing environmental condition. So we are truly fortunate to have opportunity to learn directly from Professor Owe, his experience and also insight regarding water resource management and hydrometeorological research in Indonesia. Before that, I also would like to kindly remind all participants that some materials presented today have not been published yet. So therefore, we respectfully ask participants not to take screenshot, photos, recording, or distributed the presentation material without permission from Professor Owe. So if anyone would like to use some of information, please kindly ask Professor Owe permission first. So thank you very much for your understanding and cooperation. Without further ado, let us warmly welcome Professor Owe. Professor Owe, the floor is yours.
Again.
Okay.
Okay, that's right. I'm Hiroki Owe from Ehime University, Japan. Thank you very much for introducing me, ceremonial master of ceremony, chairperson, and also Ami, who invited me to have such an opportunity, nice opportunity, to talk about this issue. If I may say myself a little bit, I have been staying in Padang this time, despite a very short period, for collaborating field research with AMI. We targeted how can we incorporate traditional knowledge into water management. So in order to improve the water management system in agriculture, not only technically but socially, we have an idea to incorporate a traditional knowledge based on our some research so far. And I have a lot of, I have been supervising over 10 PhD students in my university so far, from IPB, UNHAS, UGM, and also Andras, also USU. So I have a lot of friends in Indonesia, especially in Andras University. Also, my university, Hime University, and the university has an university to university MOU to exchange academically and educationally between researchers, professors, and the students. So if somebody have an interest in studying in my university, it is very welcome. Let me know. Okay, too many things I would like to talk before starting my presentation, but now it's time for me to start today's seminar titled Love. Because I have been informed by Ami that most of participants here has a professional subject or interested in natural resource management, all right? Therefore, among my some research subject, I selected this study, a collaborative action for sustainable water management that was conducted in South Sulawesi in dry season. Please forgive my talk about a very old story over 10 years ago when I was a little bit younger. But still, the situation and the problem or countermeasures might be applicable. I hope. So let me start now. Other than me, two people are from Hasanuddin University who supported, and collaborated with me in a field research. Okay, maybe you know very better than me about such a project. The name is Bidi Bidi project in South Sulawesi, developed by developing a dam. I remember it was in 2000, and like this way, here is a river called the Cheneberan River, and then constructing the 3 wheels, Bilibili, Biswa, and Kampiri wheel. Then the targeted area is here. Louder. Okay. Can you hear me? All right. Sorry. Oh, some message was on. Maybe please talk loudly. Okay, can you hear me now? Okay, thank you very much. Okay, the targeted area is here. The irrigation water was taken from Kampiri, a weir, and through the primary canal called Limban. And in the end of this primary canal, the rice cultivation area organized by Petiga Renga. So the object, as I talk about objectives of the study, in the end of or in the lowest reach of the irrigation system, in the dry season, how can farmers obtain water for their rice cultivation? Now I will introduce you a technical and social efforts to obtain irrigation water for rice cultivation in this Petiga R that is in the end of irrigation system. Okay, nextly, some parts already talked, the background. After BRB irrigation system developed, as I said already, as like this, a technical irrigation system was nicely or excellently developed. And plus, water master that is called as a Mandorogene, maybe in South Sulawesi, such a saucer system also arranged. A water master controls gate for irrigation. And also, one of the tasks of water master is to maintain the function of the canal. And nextly, it's a very important thing is there is a federation of the water users associations in Bahasa Indonesia, GP3A Federation. The leader of the GP3A coordinates if problems happened in some P3A consists of GP3A, coordinates and shows some countermeasure and having a discussion, maybe mainly on Friday when farmers gathered for praying. I heard such a meeting is very effective, organized by leader of P3A. I will talk about such a function by the P3A to coordinate the problems of water scarcity. So this might be categorized to social collaborative system. Okay, anyway, the problem is, despite such systems, technically and socially, still insufficient irrigation water was a problem in the lower reach in the dry season, such as in P3A Renga. So objectives, having such a background and the problems, we aimed to clarify what happened actually in the lowest reach P3A in the dry season. So the first research was irrigation and clarifying the irrigation practices for rice cultivation in dry season under water scarcity. Second one is considering the reasons of water scarcity. No need to say in the dry season, but with a very sophisticated and technical irrigation system. Why water scarcity happened in the end of the irrigation system, such as P3A Renga. Thirdly, analyzing the water balance reality here and show at least how much irrigation water should be needed, while actually how much water this area could use based on the water balance analysis. So lastly, this work showed minimum water requirement for rice cultivation and show how much water was lacked for rice cultivation in this area. So let's move on to the story about the details of this area. This area has this is just a projected area, 88.5 hectares. But practically a little bit smaller than the projected. No need to say. I will show later on by showing the map. Okay, this map shows the area managed by P3A Renga. Yes, here is the targeted area managed by P3A Renga. Red line shows the secondary channel, taking water from this primary channel. The name of the secondary channel is Pamase. Pharmacy secondary canal. And here, the last diversion, PM6. And PM6 canal, from PM6 canal, irrigation water is taken to this area, to these two ways. No, this way. This is for another. Sorry, I think it's my mistakes. There are two ways taken the water from this last diversion PM6. And plus, as I talk later, not only irrigation water through canal originated from the Jeneberon River and the Bilibili Dam. Drainage water also be applied to compensate this water scarcity. This is one of the very important points, technically and socially. Please remember how drainage water irrigation could be happened. Okay, next. Oh, so already I talk about this. Different from my, okay, this one. If I enlarge the map of this area, Renga, the irrigation water from the Pamase secondary canal, and the last diversion Bepet PM6, irrigation water is diverted. And here, I will explain from where the drainage water came. Very important. Okay, let's move on to the practical story. What was the problem? In addition to, what was the, sorry, maybe it's a little bit hard for you to listen to my voice. Now I close to my microphone, sorry. Yes, no need to say under water scarcity in a dry season. It's a very dry season. But in addition to such climatic conditions, additional problem was shown in this photograph. This was a photo at the point of PM6 diversion. That's the diversion of the secondary canal that was broken in a rainy season. So now under the process of repairing when I took this photo. So therefore, due to the, may I ignore? I can't read what, okay? Due to the broken diversion and under the repairing, very little water could be taken to this area managed by Petigan Renga, unfortunately. This is additional, but a very big problem for the reason of the water scarcity. Let me show a very small diversion. We call it a box. T means a tertiary. Coming from the PM6 canal, and here the box T1 the irrigation water was diverted to the two ways. First one is to the T2, this is a tertiary box second. And another way is to the right way on this photo to be sent to a quaternary canal. Yes, here, one way is to a tertiary canal. The other way is to the fourth, meaning a quaternary canal. And the way drawn in light blue line is the drainage water. From the next area to adjacent area of this area, the area, rice paddy field area was organized by Petiga Sapaya. This is the adjacent area to the Rengang area. From the area of Petiga Sapaya, drainage water comes through this way, and the drainage water could be recycled for irrigation by adding to irrigation water from the secondary channel. Okay, I hope you could understand very well. This point is very important. Red colored line shows irrigation water originated from the river and the Bilibili Dam. And the blue colored line shows the drainage water flow supplied from the adjacent area organized by another Petiga R. Let me show a scene of the measurement like this way, measuring the discharge. To discuss about the social problem or social issues in water management, technical measurement or scientific measurements are also needed. One of the firstly important things is to know the irrigation discharge. Nextly, observing the area size and consider whether the irrigation water is enough or not for rice cultivation in the area. Nextly, as I showed lastly, the water balance analysis. This is the way to evaluate the irrigation water problem, or whether or not enough or not enough. The water tertiary box second.
Hello. Thanks for Master of Ceremony for helping me to restart. Okay, again, good afternoon. Selamat siang. Assalamualaikum. Okay. はい。はい。
The power is off in our university, and then we next to our speaker, Prof. Owe, please.
Okay, thank you very much, Mr. Master of Ceremony. Okay, let me continue. Here is a place of tertiary box second, diverting water to the quaternary canal that is to the rice field. So measuring the discharge here also. This is the next diversion to the quaternary canal. This shows a quaternary canal. You can see the concrete lined canal, but this was after renovation. In 2012, when we started this work, this quaternary canal was earth canal, not completely lined. Therefore, not enough water could be transported to the downstream area as I show in a map. Okay, let me skip some images. This is a quaternary canal in the very lower area in this particular Rengang. Please look at this map. A green colored area was cultivated by rice. Very successfully or not successfully, that will be explained later on. In any case, this area was cultivated rice, even in rice season. And the brown colored part was cultivated by kacang hijau. So mostly rice. Next map is in the next year, 2013. Very similarly, most of the area was cultivated by rice. You can see all green, mostly green. The problem or question was underwater scarcity. How could farmer plant rice? And whether the planted rice could produce grains very well or not. Okay. Next. The three issues were investigated in the field by field survey. First one is about a secondary canal. And the second one is second water is reused water from the drainage, as I told already. The third one was the groundwater pumping. So farmers in this area utilize three types of water resources for irrigation. Normally, just the first one, that is from the secondary canal. But then, due to the problems, as I said, broken diversion, used water of drainage could function. And thirdly, farmers made the effort to utilize groundwater by pumping. Okay, please look at this map. This shows the irrigated area by the canal water. In 2012, the light gray colored part could be irrigated. But due to the effort socially and technically that was explained later in 2013, additional area drawn by a little bit dense gray color could be irrigated. Okay, what was the reason? The water scarcity, and what was the countermeasures for the water scarcity in 2012? These were listed here. Now, can you listen? Presentation again. We've already finished. Look up. Can you see my presentation? Yes. Okay, let me continue. The second one is repairing the broken Dashini canal. As I showed, this was a technical problem. Third one is the low conveyance efficiency of irrigation water in the quaternary canal. That was an earth canal. The low conveyance efficiency could not transport irrigation water to the downstream area at all. This is also a technical problem. The fourth one is a very conventional rules for water distribution. No need to say, everybody knows, from upstream area to the downstream area. Although this isn't conventional issues, but we may think that it's also social problem. Okay, from now, let me explain about countermeasures to cope with the water scarcity, especially in 2012, having a broken Atashani canal and broken weirs under repairing. So first one is drainage water recycling. Firstly, I'll talk about technical effort. As I shown in this photo, normally the drainage from the adjacent area, Sapaya Petiga A, was not utilized. normally no use. But as I say next, after the social effort, this drainage canal was arranged and cleaned by farmers under Gotong Royong. Gotong Royong is no need to say a social effort, but arranging and cleaning the canal itself is a technical effort. Okay, let me talk about the social effort to make the drainage water recycled. Discussion was held, organized by the leader of Gepetiga R, a gathering the farmers and leaders of the both Petiga Rs. Both Petiga Rs are Petiga Rengan and Petiga Sapaya. Gathering everybody under the leadership of the leader of Petiga R. Lastly, one decision was signed. The thing is this one. By taking additional water from the primary canal to the Sapaya Petiga R, then additional irrigation water in this area could produce drainage water. Then the drainage water could be transferred to the area of Petiga Renga. So do you think it is a very win-win countermeasure? Do you think? So a little bit complicated, but not so complicated. Very simple story. Here is two Petiga R. Up Petiga R, Petiga Sapaya is upper area. And the targeted area, Petiga Rengan, is down area. So irrigation water to Petiga Sapaya increased under the coordination of the leader of Petiga R, who manage all Petiga R under this irrigation system. So it is very nice and happy for the people in Petiga Sapaya because they can get more water, irrigation water, okay? And the producing an additional water for drainage in Petiga Sapaya. The drainage water can be provided to the lower area, Petiga Renga. So also, people in Petiga Renga were very glad to have an additional water sent from the Petiga Sapaya. So such a nice coordination was made under the leadership of leader of Petiga R. So I define this one as social collaborative system number one, supporting the technical issues, having a Gotong Royong. That will be explained next. Yes, Gotong Royong is every time very important, as everybody knows. This is a nice culture, I think. As a Japanese, I think that this is very nice also for Japan, because nowadays, due to the civilization and developing and the globalization, Japanese farmers, most of the Japanese farmers have a main jobs, doing the agriculture work a little. So everything could be automatically done or not focusing on the work, agriculture activity has been going on. So the population of people is decreasing year to year, no need to say, therefore, a kind of collaborative action such as the Gotonreon has been disappearing in Japan. So Japanese government set up some subsidiary or some project to promote Japanese type Gotonreon in rural area. This is an actual situation in Japan. Anyway, Gotonreon is the social collaboration system number 2. And nextly, this is a second countermeasure, extending the quaternary canal, and also not only extending but also lining by concrete. In the next year, as I wrote here, after the dry season in 2012, the quaternary canal was extended about 300, also with lining to the lower area. So the important thing is from where the fund came. The fund for this construction and activity was proposed by the leader of the village. So this means that this activity was not under Petiga A, not under Petiga Batan, Kelompok Tani. So therefore, such an, なんていうかな、social system, by mixing such a social system, the farmers could cope with the water scarcity very fluently. Not only Petiga, but in Kelompok Tani, such a system could function very well. So please look at the photos like this. This is a quaternary canal. It's a very surprising. The quaternary canal was lined by concrete. Most quaternary canal, that is called as the on-farm canal, is mainly earth canal. But by lining, increasing the conveyance efficiency, that caused the possibility to send water to the downstream area. This is a social collaborating system number 3. Okay, this is the photos. These are photos. Firstly, like this condition, earth canal, a lot of water, a lot of amount of irrigation water through this earth canal would infiltrate to the ground and could not be transported to the downstream area, but by concrete lining funded by the local government, having a proposal submitted by Kelompok Tani, the irrigation water could be transported to the downstream area successfully. Okay, let's skip. This is a story about the Gotonreon. You know very well, better than me, maybe. Okay, these are kind of countermeasures, technically and socially. Let me move on to the next story. This is about an effort by farmers themselves. privately, maybe privately. Some farmers use pumping. Important thing is that not every farmer has such a pump machine. If some farmer has a pump, other farmers ask the farmer to lend the pumping machine. And additionally, the well was constructed by the farmers themselves. Actually, I was very surprised to look at scenery during the farmer made a hole by himself. If I may say, Japanese conditions, we can't make wells up to 2 or even 3 meter depth so easily. It's very hard to make a hole. If we try to make a hole, a big stone and the rocks coming out, so it's very hard to make a hole. But here, mostly the soil layer consists of soil, sandy soil. So very important. Please remember, sandy soil. Therefore, when I looked at the activity, the farmers could make wells. I remember in 3 hours. Just in 3 hours, they made a hole by using bamboo. I was surprised to look at them. Yeah. So after that, using the pump like this, the groundwater could be irrigated successfully to their own rice paddy field. So please remember, utilizing groundwater in a dry season. So why groundwater can be utilized for irrigation? Now, dry season, okay? Now dry season. Why groundwater can be utilized? Please remember, this was also one of my questions when I realized such an activity and utilizing groundwater by pumping. So let me show the water balance schemes. I draw the water balance very simply here. Maybe it's a better for us to start rainfall, but you may think very little rainfall. Other inputs, well, I've already explained. Irrigation water from the secondary canal, PM6, and after the collaborating system, reuse of the drainage water from Petiga Sapaya, plus pumping water from the groundwater. These three, plus a little rainfall, were inputs to the rice paddy field. Nextly, outputs. First output is about transpiration, to say. Nextly, percolation and the storage water within the soil layer. This is also one of the terms for outputs. And the last output should be outflow from the rice paddy field. But based on our field measurement and the field observation, no outflow was found. So therefore, outputs were just these two, evapotranspiration, percolation, and the storage water. As I wrote the water balance equation here. Based on this equation, and the measurement of rainfall and the three irrigation from the secondary canal we use for the drainage canal, drainage water and the pumping water. And estimating evapotranspiration. I calculated last term, percolation plus storage water. I hope you could understand how I apply water balance, okay? Measuring everything in the left-hand side and measuring evapotranspiration and estimating. And lastly, as a residue of the water balance equation, I could estimate. Oh, maybe it was very hard for you to listen to, okay? Where I will show the result of water balance analysis. Before showing water balance analysis, let me show the scenery of the groundwater level measurement. Groundwater level measurements were manually. Yes, I have some sensors, water level sensor, water level sensor, that is a pressure sensors I have, but because we had 9 wells for experiment, I asked the staff to measure groundwater level every day manually. So this is a method of measurement of evapotranspiration. Very simply speaking, using the box and filled by soil, water, and rice plant in the same way as in the field, then just measuring the water level change. Oh, now the message comes. Internet connection is very unstable. Okay? Say okay. All right. Just measuring the water level. Here you can see the hook gauge or point gauge attached in the box. Then measuring the water level every morning, I could measure evapotranspiration in millimeter per day, every day. And this was applied for water balance analysis. Besides, we measured air temperature, humidity, and solar radiation, and the water temperature, soil temperature, and another by using this meteorological station. These measurements are very inevitable for water balance analysis. This is a micrometeorological measurement. All right. Let me show firstly the measurement results of the groundwater level change. This graph shows one of the groundwater level change among the 9 experimental wells. Please look at the line. This is a groundwater level change, and the vertical bar shows a rainfall. Starting from the first dry season, next is second dry, very severe dry season, and the rainy season comes here, and the first and second dry season. You can see after rainfall, to some degree, groundwater level increased. It is very clear if we look at the change in rainy season, right? The rainy season groundwater level is up to a groundwater surface. So groundwater was very full in rainy season. 0 centimeter means the soil surface, ground surface. But then after rainy season, decreasing the groundwater level like this way, and lastly, in the second dry season, the groundwater level decreased up to 2-meter depth. But please look at this part, for example. Even without rainfall, we can see a little increase in groundwater level. Can't you? Okay, this increase without rainfall was caused by irrigation. Irrigating to the rice paddy field. Now, important thing is this irrigation water came from where? You remember, right? 3 ways. But then first, the one of the 3 ways was from the groundwater. Okay? The irrigation water taken in the rice paddy field that could increase the groundwater level. Then, some farmers utilize the groundwater gained to the rice paddy field for irrigation. This wasn't very special characteristics. One of the very special characteristics, water balance in this area in terms of irrigation activity in the rice paddy field. Also, please remember what I said about the soil property, sandy soil. In the sandy soil, irrigated water infiltrate very quickly to the groundwater level. So irrigation water disappeared very quickly, but irrigation water could be provided for groundwater increase. Again, the groundwater was utilized for pumping or by pumping for irrigation. This is very interesting and one of the findings of our analysis. Okay, let me skip some very complicated story about water balance. Okay. Please let me explain about the percolation. By measuring the decreased water level in the rice paddy field, here are the measured decreased water level under fully ponded condition. Under fully ponded condition, we can estimate an infiltration to the ground. All right? So the estimated percolation was summarized the bottom of this slide. So please look at percolation loss under fully watered condition in the rice field at 5 millimeter per day under fully ponded. It's a very normal water consumption, even compared with the Japanese rice paddy field, 5 millimeter per day, plus evapotranspiration 5 millimeter. So it makes around 10 millimeter per day water consumption in the rice paddy field. And the last one is 15 millimeter per day under sparsely ponded. If this seminar will be held in front of a lot of participants, maybe I can ask somebody to answer. But it is very difficult for us to discuss such ways. So please think now, why under sparsely ponded condition much larger percolation happened? compared with under fully ponded condition. Please imagine, here we are in the center of the rice paddy field area. All paddy fields were ponded by water very fully, right? Now, the percolation to the ground is 5 millimeter per day. Nextly, let's imagine and let's change the situation. We are still in the center of the rice paddy field, but some fields were ponded fully, but some fields were not ponded, no water. So what happened? For the total percolation in this area. Now I'm talking about the total or average, maybe average or total percolation in the area base, not on a one plot base. Okay, the reason why the much larger percolation under the sparsely watered condition is that irrigated water to the plot not only goes to the vertically that would be provided to the groundwater, but also lateral flow. On the surface or subsurface. So under the fully ponded condition, irrigated water could be percolated just vertically. Only vertical direction percolation happens, but under sparsely or halfly ponded condition in the regional base, irrigation water must percolate not only vertically but also laterally. Therefore, a larger percolation happens. So, like this was my estimation. This is my own estimation. Minimum percolation in May and June, 5 millimeter per day. But in July and August, because in May and June, mostly irrigated. Most of the rice paddy field was irrigated. Not all, but mostly. But in July and August, due to the scarcity of water, sparsely irrigated. Therefore, minimum percolation was twice of that in May and June. So as a result, water requirement consists of percolation plus evapotranspiration was 10 millimeter and 15 millimeter per day. This is a minimum, not normal. So minimum means less than this one. Rice could not be cultivated. Oh, can you listen to? Okay. Minimum means less than this value, this amount of water, rice will not be able to be grown. Minimum requirement. So based on this estimation of the minimum requirement, I evaluated the present situation in the Pettigar Rengram. Okay, let me show the summary of the water balance analysis. A lot of values, so it's better for me to show very important point. Please look at the right edge, P plus delta S. This was calculated by water balance equation. The others were measured one. The others were measured rainfall, PM6 irrigation from the secondary canal. We use water from the Petiga, Sapaya, and the pumping water from the groundwater. So this irrigation was the summation of the tree and the evapotranspiration. This was measured by the lysimeter. And the last one was a residue of the water balance equation. You can see, but you can find the negative value. What negative value means, do you think? Can you understand what the negative value mean? Anybody who are now in this room? Please answer to my question. What does a negative value mean? Is it first time for you to listen to about water balance? Okay, let's study about water balance also. It's a very strong knowledge maybe for thinking about social problem. The reality must be known. Okay? Okay, so I understand your professional area, but hoping you can expand your senses. Anyway, the negative P plus delta W, delta S means the water stored in the soil and also groundwater was consumed without adding. So please imagine your bank account. Your bank account. Now this month I must pay without any salary. So then bank account deposit money should be decreased, right? This means a negative. So if I got the salary this month, yes, lucky I could have gotten last salary. This is irrigation water added to soil and groundwater. But without, or if the income was smaller than outcome, income was smaller than outcome, we must use our deposit, right? This means a negative. So looking at the water balance analysis in 2012, from May to July, even a little amount of water could be stored. But in August, stored water was consumed due to a lack of irrigation. But an even positive in May, June, and July, this was a millimeter per day. As I showed in the earlier slides, please you remember, I think that you remember the minimum requirement, minimum water requirement, 10 or 15 millimeter per day, right? So very smaller compared to the minimum requirement in 2012. But besides, very important thing was reused water that was surrounded by the blue-colored circle. As I explained already, due to the technical and the social efforts, quite a large amount of reused water by drainage could be utilized for irrigation in this year. The plus, due to the effort of farmers, pumping water was also not so small. Pumping water contributed to some degree to irrigation. And next, let me show the next year results. Okay, due to the repaired secondary tertiary canal and the diversion, PM6 irrigation through a secondary canal. All right, please compare the PM6 between 2 years. All right, this is on 2012. This was in 2013, right? Around a double of irrigation water came from secondary canal through PM6. On the other hand, although the reused water was also utilized in this year, amount of reused water was smaller than 2012, all right? Pumping water here a little bit smaller than than 2012, but then farmers made the effort to use pump. Then lastly, the yes, the right edge was P plus delta W. A little bit improved compared with 2012. But then 5.5 and 8.6 millimeter per day was very minimal. But then compared with 2012, the amount of irrigation water, thanks to the added irrigation water, especially through PM6, and thanks to the development of quaternary canal lined by the fund of local government obtained through Kerompok-Tani. Irrigation water could reach also to the downstream area. It resulted to an increased storage of water. But in August, in the same way as 2012, it was negative. So these were the reality. Even after the improvement, incorporating technical and social efforts, these are the analyzed results in my work. And lastly, some suggestions for better water management for this area. Let me skip this one. It's quite an irrigation and drainage engineering story. If I may say myself, one of my professional subject is irrigation and drainage. Or maybe this one would be better. And this was already shown, minimum percolation, and it resulted to the minimum water requirement. In the initial stage of rice planting in the first dry season, that was May to June, this was a minimum, 10 millimeter per day. And rice growing season or reproductive stage of rice in July to August, minimum was 15 millimeter per day. If I may say, the situation in Japan, not minimum, but water requirement for rice paddy field is normally from 15 to 25 millimeter per day. This depends on climatic conditions, soil properties, and the areas or some other, but it was written in the textbook for undergraduate student. Very normal water requirement in the rice paddy field should be 15 to 25 millimeter. Based on such a very text book knowledge, I thought my analysis for this area was quite reasonable, and my understanding and suggestion could be applied to improve a kind of an reliable data based on which the technical and social water management could be improved. So, like this final slides, at that time, I hoped the Petiga Rengang area that was the end of the irrigation system to exert social collaborating system to optimize water distribution. Lastly, let me show these photos. The gentleman right-hand side was leader of Gepetiga. The name of the Gepetiga is Shiranuan. His name is Den Shitaba. But unfortunately, he died in 2015 during our research. I would like to offer this presentation to Mr. Den Shitaba. Thank you very much for your attention and listening and thinking what happened and remembering some important situation or background and my ideas for countermeasures. Thank you very much. That's all.
Thank you very much, Professor Owe, for the very informative, insightful presentation. So I believe today's session has helped us better understand the importance of water balance and also water resource management, particularly for irrigation and agricultural sustainability. So now we will continue to discussion and question and answer session. For participants who would like to ask questions, please feel free to raise your hand. Before opening the floor to the offline participant, I would like to say hello to Bapak Nurfianto Giar Pangidung. So Sensei, you already have a question, one question from online participant. Can you read the question in the chat box or should I?
Through chat.
So I can read it to you. So the first question is, I want to ask Professor Hiroke, how can irrigation governance frameworks effectively balance top-down state regulation with bottom-up community participation to prevent the irrigation efficiency paradox, where improving on-farm water use efficiency using drip irrigation and sprinkler irrigation fails to reduce total basin scale water consumption and can actually increase water consumption, worsening overall water scarcity rapidly?
Thank you very much for your question. There includes some issues. Firstly, about other type of irrigation system, such as sprinkler or something, are for upland crops, not for rice paddy field. So therefore, for this for today's talk, I can't understand what you want to ask me in terms of an certain irrigation method. Setting aside this one, if I read your questions, a governance frameworks effectively balance top-down state regulations with bottom-up community participation. Top-down here or in any agricultural and rice cultivation area, it should be based on the Petiga system, all right? The Petiga system was introduced by the government firstly. And then this is one of the research issues with our cutting down.
Are you comfortable to listen to? Petiga system is a kind of a top-down system. This is one of the issues that I and Ami are working on. In some areas of West Sumatra, this top-down system Petiga can't function very well in terms of the balance between the traditional culture and the top-down system. But in South Sulawesi, my impression is that this top-down, a kind of a top-down system, Petiga system, could function very well. But this system based on the base of very social collaborative system, such as Gay Petiga and meeting organized by leader of Gay Petiga gathering all leaders of all Petiga gathering and discussing about the problem of water use, not only irrigation issues, but also when shall rice plant be started in this season, or what rice variety might be better to be selected. Such an agronomical and irrigation technical issues were discussed in the meeting. And plus, because now I'm a Japanese and I have no religions, so I'm not sure very well. So if I made a mistake, please forgive me. The things that I interviewed there, I was very interested in. That was such a meeting organized by leader of Gay Petiga was mainly held in some Friday. After praying, everybody gathering and discuss very friendly. And all farmers, including a leader of Petiga listen to the talk of the leader of Gay Petiga because this opportunity is after praying. So I was very interested in and I admired their culture. So even the system was top down. By arranging and then making a balance between their own culture, I think that it is possible to function, to make the system function. This was a part of academic understanding when I did this research. Does this story make an answer to your question? If no, let me know or make additional question. Thank you very much.
Okay. Thank you very much for your explanation, Oe Sensei. So now because we are in the Q&A session, so for participants online and also offline who would like to ask question to Oe Sensei, please feel free to raise your hand. Oh, okay. So we have one question in the chat box, Sensei. Is from Farhan. So Professor, my name is Farhan and I am a student from Andalas University. I want to ask Professor Hiroki, in your discussion, cooperation between farmers group appear to be crucial. Could you elaborate on what key factor help build and maintain trust among this group?
Thank you very much for your question. It's a quite difficult issues. How to continue and how to build. Because this is just a story that I listened to from one of the farmers, and I remember I heard this one from again Denshitaba-san or somebody. But one thing, under the system of Petiga R, every farmer, including a leader of Petiga R, and everybody trying to improve the system, and also they try somehow cultivating rice even in dry season for their living. Therefore, applying to a local government fund. If I don't know very well about certain ways to propose. The fund of local government cannot be from Petiga R, but from Kerompokitani or village. So as I said, maybe through any route, they tried to improve their system. So in order to improve the quaternary channel or tertiary channel technically, no need to say a fund is needed. So what can they do? One of the possible way was to apply the local government fund through Kerompokitani. So I think that the communication between the Petiga system and village system based on the nice or friendly relationship between leader of Betiga R and leader of village could make it happen, I guess. In any case, I have learned that such a social collective system might be very important without this type of improvement for water management should not be so possible. So I'm not sure very exactly, but very nice and friendly relationship between political system and the village could continue or could make the improvement possible. This is my understanding. Maybe it's not a complete answer for your question. Now this is what I can tell you. Thank you very much.
Thank you very much, Owe Sensei. So, Farhan, is it you do want to ask something or is it okay?
Okay, thank
Okay.
you, Prof. Thank you.
Okay, thank you, Farhan. So, yeah. So everyone who have question, please raise your hand. And I believe many participants here come from different scientific background, including agriculture, environmental, and engineering also. So please do not hesitate to share your thought, maybe, Sensei, right, Sensei, or ask question to Oe Sensei. So before we come to online participants, I would like to ask offline participant here in Pasca. Do you have question for Oe Sensei? Yosti, Ui, Tegar?
Oh, okay. Thanks, sir, for the presentation. I will ask, do you think the modern technology alone can solve water problems, or is social collaboration still the key picture? Maybe it's my more clearly. Do you think modern technology alone can solve water problems, or is social collaboration still the key factor? Okay,
Thank you
so
very much.
thanks.
What do you mean by modern? What do you mean by?
In irrigation system, water resource.
For example,
What's marine? Yeah, not traditional. Yes.
so for example, what modern? Applying what?
Pump. Yeah.
Oh,
Yes.
pump,
Pump.
pan, pump the show. Then using pump, I have already explained, right? No. But an important thing, if if I add some explanation about the pumping irrigation for rice, without knowing the water balance situation, or reality, it can't be applied at all. As I said, the irrigated water will be infiltrated to the ground, also provided to our groundwater quickly due to the sandy soil. Therefore, and it is one of the disadvantages for saving water in the rice cultivation, don't you think? Very quick calculation. This is a very large consumptive water. So one of the disadvantages for saving water, right? But on the other hand, this was an advantage because the irrigated water and the percolated water could make a water resources again, right? I imagined at that time, observing this such a reality in the field for water management by using pump, I realized that everybody living there, including the farmers, know the water balance, not theoretically, but practically. So because they know very well, therefore they introduced pumping irrigation, I thought. Except for certain sort of properties or without certain water balance characteristic, using groundwater would be not so possible. One of the reasons why they know certain water balance, not theoretically, but based on their experience, is that they utilize groundwater for their living every day. So they look at the groundwater level. Therefore, groundwater level down now around 2 meters, but the irrigated water comes to the rice paddy field adjacent to their house. Increased. Maybe I guess that they observe such a natural environment by themselves. This is very important. Knowing the natural environment and the phenomena, then applying the irrigation practice technically and also socially. This was my one of findings in this research. Thank you very much.
Thank
Thank you, Professor Owe. So, is there any from 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 what?
This nyambung sama pertanyaan newspaper.
So the other question is also come from Nurfianto, Bapak Nurfianto. I want to ask more related technology in rice water management, such as alternative wetting drying to increase water use efficiency and reduce GHG emission from rice field, such SRE method and using smart sensor. Is it possible with our P3A irrigation system? Is it economically feasible? And maybe any best practice or implementation this technology in Japan? Thank you.
Thank you very much for your important question. Water saving irrigation, such as SURI, can be applied under the condition of very sufficient irrigation water. It's very important. With sufficient water resources, then water saving planting system can be possible, can be happen, all right? Because there are some growing seasons when the rice needs a lot of water. But some seasons or some growth seasons without water, or even without water, rice can grow, or without water, it's better for rice growth, right? So in order to make certain irrigation management happen, a quite sufficient amount of irrigation water is needed, right? Otherwise, like this rice cultivation area in Rengang Petiga are, there were not so enough water even in the growth stage when rice do need water, right? But this is very important. I think that an water saving irrigation can be applied with a very sufficient water. Secondly, related to the story, there are some rice growth stage when rice does not need water, or even without water, rice can grow better. This is the season, the growth season. Maybe you know very well, to stop tillering. This is called as an intermediate drying stage. Because if under free watered condition, rice plant increase the number of stems, it is not good for producing rice grain. So this tillering, number of tillage must be stopped by drying, right? This is originally from the viewpoint of agronomical management plus water management. Midsummer in Japan, midsummer drainage or intermediate drying. So this agronomical water management or agronomical management could be also function to stop or to decrease the methane emission. Maybe you know very well, methane is emitted from the rice paddy field under watered condition because no oxygen in the soil. The carbon will be, I'm not in chemistry. My profession is not chemistry, but under very small, under the scarcity of oxygen, carbon will be turned to be a methane, right? Methane is a very strong greenhouse gas, all right? So by stopping irrigation or stopping the tillering, this was called as a midsummer drainage or intermediate drainage, as I said, originally from the viewpoint of agronomy, is very effective to decrease the methane emission. In Japan, this drainage is highly recommended for any farmer from the viewpoint of decreasing greenhouse gas emission. But then, as I said, most of the farmers in Japan have the main jobs other than agriculture. Therefore, it's not so easy for them to stop irrigation water so long. But
Japanese government recommended rice farmers to continue the drainage, to keep the drainage condition, to keep the without water conditions longer than 1 week. It's not so easy for most of farmers who have a main job. Anyway, I want to say is that with an sufficient irrigated water resources, then water saving irrigation system can be applied. And also it is very effective to stop greenhouse gases emission, especially methane. This is what I know. Under the very limited understanding and knowledge, these are what I know. Thank you very much.
Thank you very much, Sensei, so for the insightful information and also in terms of academic perspective, Sensei. So my apologies because of time limitation. We have to conclude this lecture session. So thank you very much, Professor Owe, for the excellent presentation and also discussion today. We also certainly thanks to all participants for the active participation and thoughtful question. We hope this discussion inspire future research, collaboration, and innovation related to water management and environmental sustainability. Once again, thank you very much to Professor Owe and all the participants. Have a wonderful day and see you in the next academic session. Assalamualaikum warahmatullahi wabarakatuh.
Thank you very much for everybody to give such a very nice opportunity for me and giving a very nice question with which I can add my my own questions. And this could give me a nice opportunity to think more academically, scientifically. Thank you very much. See you again somewhere.
Thank you, Sensei.
Okay, thank you, Miss Ami and Mr. Owe. This agenda till the end, and we close with Alhamdulillah. And to everyone, audience, thank you for coming and waiting for the next session and lecture and learning session series. We monthly event is there is different topics again. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.